Look at the pristine geometry of a digital blueprint. Now, lay that perfect abstraction over the chaotic reality of an active construction site. There is an immediate and severe collision between what is planned digitally and what actually happens in the mud and steel. For decades, quantity surveyors have acted as reactive accountants. Their job is to estimate massive project costs and material requirements based almost entirely on interpreting flat, two-dimensional geometries. Calculating three-dimensional volumes, like thousands of cubic yards of muck excavation or complex structural steel layouts, from paper cross-sections is notoriously tedious. It invites severe human mathematical error before the first shovel ever hits the dirt. The construction industry is now moving away from this retrospective guesswork. Cost estimation is becoming a proactive, data-driven engineering discipline. This relies on the implementation of cyber-physical systems. By continuously linking live digital data streams directly to physical assets on the ground, engineering teams can aggressively eliminate both spatial discrepancies and financial risk. To understand how these systems operate, we rely on Paul Milgram's reality-virtuality continuum. This animated diagram structures the technological spectrum, running from absolute physical reality on the left to fully synthetic virtual reality on the right, with augmented and mixed reality occupying the space between. On the far right axis, virtual reality completely occludes the physical world, creating a fully synthetic environment. Because it isolates the user, it is primarily deploying during the early pre-construction and planning phases. The center points of the axis represent augmented and mixed reality. These tools maintain the user's connection to the physical environment, blending digital data directly over the real world for use on the active job site. Extended reality eliminates the superficiality of traditional architectural rendering. It serves as a precise structural mechanism that a multi-trillion-dollar industry uses to manage hard financial and spatial risk. Before any ground is broken, estimators must draft the preliminary cost plan. The accuracy of this early forecast dictates the financial survival of the entire project. Anticipating logistical risks, like staging materials on a steep gradient, historically required decades of accumulated physical intuition. A junior quantity surveyor looking at a flat 2D floor plan will consistently struggle to translate those lines into real-world constructability constraints and safety hazards. Virtual reality solves this by pulling massive digital datasets from cloud-based common data environments directly into fully occlusive headsets. This generated image places us in a first-person perspective inside a one-to-one scale mechanical room. These color-coded pipes and ducts possess true physical volume and depth, allowing for precise spatial interrogation. Geographically separated engineering teams can inhabit this exact same digital model simultaneously, conducting immersive design reviews from anywhere in the world. Once inside, users can toggle specific structural layers on and off to expose hidden clashes between mechanical, electrical, and plumbing elements. Resolving these conflicts physically at true human scale captures ergonomic nuances. A surveyor can literally verify if a maintenance worker has the spatial clearance to access a specific valve, a detail that automated clash detection algorithms routinely miss. Moving a pipe 3 inches in a virtual environment costs nothing. Moving a welded steel pipe 3 inches on a physical site incurs exponential rework costs and severe scheduling delays. By visualizing the true scale of the build, VR effectively neutralizes the experience gap. It ensures that contingency reserves and labor forecasts are based on the physical realities of the site, rather than theoretical assumptions. Once construction begins, the objective transitions immediately from design validation to strict execution accuracy. The model must meet the mud. Augmented reality accomplishes this by superimposing two-dimensional schematics or 3D models onto the real world using the camera screens of consumer mobile devices like tablets. Mixed reality takes this further. Using advanced stereoscopic headsets equipped with depth sensors, MR systems continuously scan and map the complex physical geometry of the room. This capability allows digital objects to anchor dynamically to physical coordinates. In this MR viewpoint, a digital glowing HVAC duct physically occludes behind the real concrete pillar. The virtual object behaves as if it exists in the physical space, allowing for natural hand gesture manipulation. Below the ground surface, advanced AR systems combine with high-precision global navigation satellite systems to project subsurface utilities. Excavation crews are granted equivalent X-ray vision. By seeing undocumented high-voltage conduits projected directly onto bare dirt, they can guide stakeouts and confidently avoid critical, dangerous utility strikes. The efficiency gains here are highly quantifiable. Researchers at Stanford University modeled the impact of mixed reality on resolving field-detected mechanical issues. This bar chart compares conventional overhead against an MR integrated protocol. Moving to MR inspections dropped coordination overhead by 75%. Additionally, a line graph tracks the project timeline. With spatial constraints visible, the time to resolve complex issues shrank by half. AR and MR physically pull the as-planned model out of the office. They serve as a relentless visual validation mechanism against the as-built reality. All of this spatial precision ultimately serves the financial engine of the project. For the quantity surveyor, the most friction-heavy responsibility is managing interim valuations and authorizing contractor payments. Accurate work-in-progress reporting is the lifeblood of construction. If cash flow stalls, the project dies. The traditional workflow requires an estimator to walk a sprawling site and visually guess the completion percentages of various trades. This subjectivity leads to massive, costly disputes between contractors and clients over exactly how much work has actually been executed. Augmented reality removes the guesswork, transforming interim valuations into an objective, data-driven transaction. Watch this data pipeline. On the left side of the screen, a site superintendent sweeps a tablet over newly installed structural elements, verifying their physical presence. Marking an element as completed automatically attaches geotagged photos and timestamped metadata directly to the 3D object. Over on the right, the cloud server syncs this verified field data into the digital bill of quantities, updating completion metrics in real time. For the surveyor sitting in the office, this provides instantaneous, undeniable visual and quantitative proof of exactly how much material is in the ground. The financial return on this tracking is severe. Subsurface tracking platforms have generated 20-to-1 financial returns by catching scheduling misalignments early enough to prevent downstream cost overruns. By automatically rolling up field-verified quantities into exact pay items, extended reality tools establish a transparent financial record that reduces contractual friction. The software capabilities are profound, but the global implementation of these tools is highly fractured. While heavily capitalized markets in North America and Europe rapidly integrate digital twins, emerging markets struggle with stagnant, conventional methodologies. Look at empirical data from the Sri Lankan construction sector. It highlights a massive disparity. 56% of professionals possess a working familiarity with these technologies, yet a staggering 78% of that informed group have never applied them to an active project. This stagnation is driven by 4 systemic barriers: severe upfront capital constraints for hardware, a pronounced deficit in specialized technical expertise, deeply entrenched cultural resistance to changing legacy workflows, and the lack of robust cloud infrastructure on remote sites. Overcoming these barriers requires a rigorous, phased roadmap. It begins with strictly controlled, localized pilot studies designed to generate contextualized return on investment data, proving the financial viability to legacy contractors. Software capability alone cannot override economic and cultural realities. Successful automation requires highly localized, strategic implementation frameworks to take root. As the industry matures beyond 2026, modern visualizing techniques will merge with predictive artificial intelligence. This generated tracking shot demonstrates an autonomous inspection framework. AI algorithms actively process the live video feed directly from an inspector's headset. As the surveyor walks the site, the system automatically detects assets, assesses installation quality, and visualizes pass-fail results instantly. These live insights feed directly into digital twins, living replicas of the physical building. The AI will automatically predict mechanical failures based on vibration data and trigger advanced material procurement orders before a human ever types a keystroke. The professional value of the quantity surveyor resides in the capacity to orchestrate, analyze, and strategically interpret the vast automated data streams flowing through the cyber-physical site.